Last chapter, we were up in the stratosphere with free energy and spontaneity and entropy, and we're going to come back down to Earth and talk about something practical, electrochemistry. Let's see, do I have everything except for this? Camera walking around. All right. I think at some point in the past, we've introduced the concept of oxidation and reduction. But if I haven't, then here it is again. Well, first of all, electrochemistry is simply the chemistry of electrical energy being exchanged for chemical energy. So when I hear electrochemistry, I think batteries. Now, as far as oxidation reduction goes, and we abbreviate that redox, probably because oxyred just doesn't sound right. Oxidation, I think I have yeah, there it is. This is a little acronym, oil rig. If you don't already have it memorized, oxidation is loss. And by that we mean loss of electrons. Let's try it again. Loss of electrons. Reduction is gain of electrons. So anytime you have movement of electrons in a chemical process, you've got oxidation reduction. Now, if we have something that has lost electrons, and the reason, okay, let me back up. Oxidation and reduction always occur together. You can't have one without the other. So if one species loses electrons, another one has to gain electrons. And we say this species is responsible for this reduction. So that we call the reducing agent. The one that's oxidized causes the reduction of the other one. And the reduction of this one causes the oxidizing of the other one. Okay, I'll put that in a sample reaction here in a minute. In order to determine whether or not you have an oxidation reduction reaction going on, you've got to be able to somehow quantify the movement of electrons. So we have these rules, and these rules don't always represent the actual excess of electrons or less electrons in a species. It's just a bookkeeping scheme. So we look at these oxidation states in a chemical reaction, in all the species in a chemical reaction. We look at their oxidation states so that we can look at the elements on one side, reactants and products, and see if their oxidation states have changed. If they have changed, then we know we've got a redox reaction. So the first one is the simplest one. Oxidation state of an atom in its most stable elemental state is 0. So it's like this is a neutral atom. We're giving it an oxidation state of 0. If we have an ion somewhere in our mix, then that ion has the oxidation state of its charge. If we have oxygen in a covalent compound, now we have to assign oxidation states for elements that are in covalent compounds, and we know that they only share electrons. They don't give them up completely. So for this one, since oxygen is is in so many reactions. We're going to nail this one down. If oxygen is by itself in a covalent compound like water, that oxidation state for that water is -2. Okay. The exception to that is peroxides. If we have this compound, hydrogen peroxide, then that whole group is -2, so each one is -1. Okay. And I've got some examples there of peroxides. Hydrogen in a covalent compound, if we write it as if it were, remember when we were naming compounds, we used the type 1, type 2 format for our type 3s, but our type 3s never had ions. But we always put the first one in the name, and in the compound occupies the cation position, right? So it's going to be, now that we're talking about oxidation states, this first position is positive. And you can calculate it from this, of course. This is going to be +1 for each one of those. But even if hydrogen is in some other compound, if it comes first, or if it's not attached to a metal, let's put it that way. I think that's a better choice. If it's not attached to a metal, then it will be a +1. If it's attached to a metal, then the metal's positive tendencies take precedence. So our example there was aluminum hydride. It's in the second position, which means this is 3+, and this would be -1. In those cases, hydrogen has an oxidation state of -1. Then we come to the halogens. We can say with fair certainty that fluorine in any compound has an oxidation state of -1. Whether it's an ionic compound or a covalent compound, fluorine will be -1 always in a compound. The other members of the group, chlorine, bromine, iodine, astatine, it depends on whether we have to assign an oxidation state to them in order to proceed. Sometimes you have elements in a compound that are not covered by these rules. So then you have to decide which one are we going to fix so that we can calculate the others. Right? And halogens are one of those. We'll come across some examples in a minute or two. If the compound is neutral, for instance, like water, if it's neutral, then the oxidation states of all the elements must add up to 0. If you have a polyatomic ion, though, then the oxidation states have to add up to the charge. If you have an alkaline metal in a compound, it's always +1. If you have an alkaline earth in a compound, it's always +2. And those are typically, well, they're always ionic compounds anyway. If we have to assign an oxidation state to chlorine in order to proceed, then, for instance, phosphorus pentachloride, right? We don't have a rule for these. So in this case, rather than speculate about phosphorus, we're going to go to the halogen as -1. That makes this one +5. Cyanide ion. Cyanide ion. All right, in this case, carbon can have oxidation states. It can have 8 different oxidation states. Nitrogen is not quite as many. So we choose nitrogen in this case as a -3. So if you look at here, these are -1, -2, -3. We learned those when we were naming compounds. If we make that one -3, then in order for this one to leave us with a negative, that means we only have to balance -2 out of that. And that leaves one negative excess. Then this one is +2. Okay. All right, some examples. Potassium dichromate. All right, so we have rules for oxygen and potassium. All right, so this is going to be a +1. This is going to be a -2. We have to calculate chromium. So the total here would be -14. 7 times -2. Total here would be +2. So these taken together means we have -12. It has to be balanced by those two chromiums. That means each chromium must be a +6. It's just half of the +12 that's required would be +6. Okay. Now we have a polyatomic ion, right? The carbonate ion. We have a rule for oxygen, -2. That's -6 total there, but we need 2 minuses left over after we neutralize it, after we balance it. So we only have to balance -4s. This is a +4. Manganese dioxide. Right, so this is -2. That's -4 total. It's neutral, so this has to be a +4 because there's only one of them. PCl5, we already did that one. And sulfur tetrafluoride, we do have a rule for fluorine, right? So that's -4 total. This one has to be a +4 to balance it. All right. And this oxidation states are very useful for tracking redox reactions. This is not the only possible bookkeeping scheme for movement of electrons and assigning polarities for covalent bonds. And I had it in my brain just a second ago. Well, there are other methods. We're going to use this one. Okay. We have an example here of a reaction where we have hydrogen ions, right? So that means this solution is acidic. Okay. We have the manganate ion. We have iron 2+ ions in solution, and they react and produce manganese 2+ ions, iron 3+ ions, and water. One thing you'll notice about this reaction is there are some missing components. They're spectators. We just leave the spectators out. MnO4-, it could be a potassium, could be a sodium, probably to get it into solution. Iron 2+, possibly chloride or nitrate, but we leave those out because they don't participate in the reaction. It just makes for a cleaner setup. All right. So these reactions can be, we can extract the half reactions, the reduction reaction and the oxidation reaction from the overall reaction, as long as we know how the electrons are distributed. And for the reduction reaction, the electrons go in as a reactant. For the oxidation step, the electrons come out as a product. Because somebody's losing something, so it's got to be as a product. Reduction, they're gaining those electrons, has to go in as a reactant. Now, how did we end up with 5 electrons there as the possibility? Well, we're going to go to an example here in just a minute, but I will point out that the number of electrons going in has to be the same number coming out. They have to balance. And that's one of the steps that we're going to use when we balance equations by the half reaction method. So if you're given an overall reaction that's unbalanced, and you recognize it as an oxidation reduction reaction, then this technique is useful and saves you a lot of time. My budget method works for a large number of reactions, but it's easier and quicker to use this method when you recognize an oxidation reduction reaction. Okay, so what we want to do is, once we've got the overall reaction, we want to assess the oxidation states and determine which species are reduced and which are oxidized, and then put them in their separate reduction steps and oxidation steps. And then we go through a balancing procedure where we balance all the elements except hydrogen and oxygen, right, because of water. And then we balance the oxygens using water. And then we balance the added hydrogens. We have to add hydrogens when we add water. So we balance the hydrogens with H pluses. And then we balance the charge using electrons. And once we got that far, then once the electrons are balanced, then we can combine the reactions back into a whole and do whatever else we need to finish balancing. All right, so there it is as a flow chart. Take it or leave it. Let's do this one as an example. We've got this is our given, let's see, that's 2. This is our given reaction. These are all in aqueous solution, so I'm going to leave that out. The sulfide ion then yields Cr3 plus and SO4 2 minus. By the way, how do you recognize an oxidation reduction reaction if you need to do it quickly? Well, one rule of thumb is, if you have an element on one side, let's say we're going to react sodium metal with chlorine gas, right? And we're going to get table salt. Okay, it's not balanced yet, but we're just trying to recognize oxidation reduction reactions. If you have an element on one side and you find it's wound up in a compound on the other, then you definitely have an oxidation reduction reaction. That can save you a lot of time. If the question is just, is this or which is, then you can knock those out. Now, if you have any that don't have that element compound type, then you have to go to the old-fashioned way. Okay, so the first thing we have to do is separate them into half reactions, but in order to do that, we got to know what their oxidation states are, right? So here we have a -2 for oxygen, so that's a -14 total. We're going to hold out 2 negatives, so we only have to balance these 12. That means this one is a +6. So far? Okay. -2 for this is -6 total. We have to hold 2 minuses out, so we only have to balance a -4 +4. And you can check yourself to see if you've still got the -2 charge. That chromium's already given. It's a 3+. This one's -2 times that is -8, and we're holding 2 negatives out for this charge, so this one is a +6. Now we have all our oxidation states. Chromium decreased its oxidation number, which means we had to add negatives. So this chromium was reduced by addition of electrons to this chromium. So the reduction step here is going to be this compound. I'll try to keep it lined up. I'm going to go keep that up there for now. And it goes to this one. Okay. That means the oxidation step must be the sulfite, so +4, going to sulfate, +6. Okay. So we've separated and we got everything from up here down here in these separate steps. Now we want to balance the non-hydrogen oxygens. Right, we've got an oxygen here. We've got 2 chromiums here. We need 2 chromiums there. We got 1 sulfur here, 1 sulfur there. We're good. Now we want to balance the oxygens. So we got 7 oxygens on this side. We need 7 on this side. There's our 7 oxygens. But we added 14 hydrogens. So we have to put 14 hydrogens on this side in order to balance them. Okay. We have 3 oxygens here and 4 there. That means we only need 1 more oxygen. But by doing that, we added 2 hydrogens. Okay. Now, let's see, we're following along here. So far, so good. Oh, we've got to do electrons next. Okay. So if this is the reduction step, we need electrons in here. So how many electrons do we have to add to go from a +6 to 2 3 pluses? Well, to go from one chromium +6 to 3, that means we have to add 3 electrons, right? But we got 2 of them, so that means we actually add 6 electrons. And for this one, we lost 2 electrons for each one of these sulfurs. Okay. All right. Now what we have to do is balance the electrons. And let's see. Wait a minute. Oh, I put water on the wrong side. Sorry. We got 3 on this side. We got 4 on that side. So that means we need water on this side and 2 hydrogens on this side. You probably noticed that, you just didn't say anything. That didn't change the electrons. So now we can balance the electrons. How do we get the same number of electrons? Well, in this case, if we multiply this whole equation through by 3, we'll get 6 electrons. So our multiplier here is 3, and then 3 here. That makes 6 here. That makes 6 here. And that makes 3 here. Okay, so now we got the right number of electrons. We can combine the equations. Bring them back into 1. So let's see, I'm going to put this one first. CR2O7, 2 minus. Then I'm going to put 3 sulfite ions. Let's see. That one, that one. Now I'm going to bring down the water. Okay. And I'm going to bring down the hydrogens. And the electrons, we don't need to bring because they cancel. Okay. Now, by the way, later on, when we calculate voltages for cells, you'll need to know how many electrons, how many moles of electrons were actually transferred. Right, so when you balance one of these equations, remember that number. But for what we're doing now, they cancel. Then we got 2 yields 2 chromium 3 plus, and then here, and then 3 sulfate. Right there. And then we did water next, didn't we? Plus 7 water. And then 6 hydrogens. Okay. So now we can reconcile excesses of one or the other on either side. We've got 3 waters here, 7 waters there. So 3 of these cancel, and that leaves us with 4 waters on that side. And hydrogens, we've got 6 on that side, and 6 from 14 is 8. So that should be our balanced equation. So just checking. Yep. That's our final balanced equation. Now notice that this has to be in acidic solution because of those hydrogens. Not all reactions occur in acidic solutions. Not all redox reactions occur in acid. Some of them occur in base. So if we were to conduct this reaction in basic solution, we use what I call the fake acid method. You do the acid first, then you convert it to basic. And to do that, you neutralize these hydrogen ions with hydroxyls. I've got more slides on it, but this seems appropriate. So if I add plus 8 hydroxyls on both sides, right, then what does that give us? That gives us 8 waters, right? Okay, so now we get rid of these waters on that side, and we end up with 4 waters on this side, plus our hydroxyls. And these go out because they were used up in that term. So this would be in basic solution. That doesn't mean that the reaction will proceed very well in basic solution, but this is an exercise in conversion. And always remember that as written here, all these components are in the same matrix. They're in the same solution. Right, so even though they're on one side or the other, they're still in the mix. Okay. All right, we got one more here. As an example. Let's see if it's I constructed the slide so that I don't have to write it on the board. That'll save some time. So we've got bromide ion, manganate ion together yield bromine, liquid, and manganese 2 plus. We know this is redox. Why? Because we've got an element on one side and it's an ion on the other side. Okay, in acidic solution then, we want to separate those out. Oops, I didn't do it that way. Okay, so I'm gonna have to do it the hard way. And these are all aqueous. Yeah. MnO4 minus and bromine. Well, that's liquid. And manganese 2 plus. I might as well write these in. There we go. Okay, so that's a -1. This is -8. Hold one out is -7. This is a +7. This is 0. And that's a 2 plus. So we know the reduction is the one that went decreased its number. because we add negatives to it. So +7 to 2 plus is our reduction step. Okay. And 2 plus. Okay, so the oxidation must be the bromide ion going to bromine. Okay, and that makes sense. This is 0, that's minus. How do you get to a 0 from a minus? You lose one of the minuses. Okay, one manganese, good there. One bromide, two diatomic, that means we need two of those. We don't have to balance oxygens with this one because there aren't any. But we do have to balance these 4 oxygens. So we have 4 H2Os here, and that means 8 hydrogens. Okay. Now electrons. If we go from a +7 to a 2 plus, and there's only one of them, that means we had to add 5 electrons, correct? Okay. For this one, we go from -1 to a 0, which is lose 1 electron, but there are 2 bromines. So we actually lost 2 electrons in that process. Okay. I know why this one's in here. Because we got 2 prime numbers. An even and an odd. So how do you balance that? Cross multiply. So I take that 2 and put it up here. And I take that 5 and put it down here. So that gives us 16, 2, 10, 8, and 2. It gives us 10 here, and 5 there, and 10 here. So our electrons balance. And we can bring it down. So let's see, let's put it in the same order. 10 bromide ions and 2 manganese tetroxide, and then hydrogens. Okay, 1, 2, 3. 1, 2, 3. These go out. On this side, we have 5 bromines first. Okay, and then we have 2 Mn2 pluses. Okay, and then we have 8 water. Okay, now can we reduce that any further? Only water on that side, only hydrogens on this side. We can't divide it by anything to make it smaller because there's a 5 here. Okay, so that's it. That's our balanced equation. Let's see if it agrees. 10, 16, 2, 5, 2, and 8. Okay. It takes practice. And extra care, because there's so many steps. The more steps you have, the more possibilities for errors. This will be a good test for cognition as you age. Okay. These are the written instructions for basic solution balancing, my fake acid method. Balance it as an acid equation and then convert it to basic. Those are just the added steps. Okay. What if we started out with OH minus instead of hydrogens? What are the possible problems that could arise? I'm not saying it can't be done. I just think it would be more difficult. You'd still have to add, well, if we did waters first and then we tried to balance it with hydroxyls, since water is a ratio of 2-to-1 for hydrogen oxygen and hydroxyls are 1-to-1, then you're going to have an endless loop. You're going to be going forwards and backwards just continuously, and it would be difficult to balance it. So I think the fake acid method is probably your best bet. Okay. Balance the following in basic solution. Let's see. Does this give the answer or does it? Yeah, it just gives the answer. Do we need to do this one? Might as well, since it's being recorded. We get it all in here together. MnO4. And then MnO2. Now, there are a whole host of reactions that occur in basic solution. Dry cell batteries, for instance. Right? They call them alkaline batteries for a reason, because the reactions occur in basic solution. It's kind of a paste, but it's still a solution. Dry cell should be in quotes. They're not really dry. Okay, so we're going to say that nitrogen is a -3. So that means this has to be a +2 in order to balance and give us a negative there. We did this one before, I think. 2 is a -8, 7, -7, +7. And here we've got two assumptions. Oxygen's already got an assigned value. Nitrogen then would have to be -3. So that's a -5, and we hold out 1, so -4 is all we have to do for this one. And then this one is +4, right? -2 times 2 is -4. Balance with a +4. Okay, now reduction step. Manganese goes from +7 to +4. Okay. And then the oxidation step must be the cyanide. +2, 2. I don't even know which this one's called. All right, balance oxygens. We have 4 on this side, 2 on that side. We need 2 more oxygens on this side. That means we have 4 hydrogens on this side. Okay. We have 1 oxygen there. We need another oxygen over here. And that means we need 2 hydrogens on this side. Okay. Now, electrons. How do we get from +7 to +4? We have to add 3 electrons. Right? And since there's only 1 manganese, that's all we need. I got a straight thread here. This must make it look funny. On this one, we had to lose 2 electrons to go from a +2 to a +4. Okay, now we have to balance a 3 and a 2, cross multiply. So we have 3 here, 3 there, 3 there, 6 there, 6 there. And then this one's 2 times 4 is 8. And then 2, then 6, and then 4, and then 2. Okay, electrons cancel. And bring it down. Let's do the cyanide first. 3 Cn minus, and then the 2 MnO4 minus. There. And the waters. There. And then hydrogens. And on this side, we'll do this one first. CNO minus. Then we'll do 2 NNO2. I smell pizza. Maybe I'm just hungry. They were supposed to have pizza next door, but I don't think I was here when they were doing it. And let's see, M4, and then water. And then hydrogens. 6H plus. Okay, so we have two choices, right? We can go ahead and neutralize the hydrogens, or we can clean it up first and then neutralize the hydrogens. Yeah, 6 of one, half a dozen the other. I've never done it, neutralize the hydrogens first. So maybe I'll do it that way this time. So we need 8 OH minus here. That means yeah. And in order to do that, we need to know which one's the biggest one, because that's the one we want to make balance. This makes 8 waters. And 8 over here gives us 6 waters and 2 OHs. Right? That kind of complicates things. Okay, so we've got 6 plus that is 10 waters and 3 waters on this side. So those 3 go out and we're left with 7. And then, oh, I forgot about these 8 waters. All right, let's start over again. That makes 11 waters on this side, right? And 10 on this side. So these waters go out and we're left with 1 water on this side. There we go. So now let's see if we have any repetitions. 2 hydroxyl. Okay, let's see if that agrees with what I've got on the board. 2, 1 water. Yep. 3, 2, and 2. Okay, so it worked. I think it was messier though. If it was me, I wouldn't do that again. I go through and clean it up first and then make the conversion. Be less likely to make mistakes. Okay, so that's balancing equations using the half reaction method, both for acids and bases. Now we're going to actually do something with these reactions. We're going to extract energy from spontaneous processes. And to do that, we need what's called a galvanic cell. It converts chemical energy into electrical energy, also known as a battery. So the reaction has to be spontaneous in the forward direction in order to produce a current. There's just one problem. Up to this point, our reactions have been balanced in a mixture in one vat of solution. Right? How do you get access to those mobile electrons? Well, if you leave it in the vat like that, you don't. Those electrons move and they probably generate some heat. Right? We want that heat energy as electrical energy. So in order to do that, we've got to separate those two reactions, put them in separate vessels, and then connect them so that they have access to the electrons that are moving. And we also have access to those electrons too. Right, so here's how we do it. These are two possibilities. A galvanic cell has the reduction step in one vat and the oxidation step in the other. And we connect them through an external circuit between those two electrodes. That's where we access the electrons. And then you haven't had physics, right? Or physical science? in the physical zones. In order to get electrons to move, they have to move in a circuit, right? And that's circle. So if the circuit is broken anywhere, electrons will not move. So electricity in your house, how do we do that? Because we've only got power lines coming in. We don't have any ground lines coming out. We go to earth. We use the entire earth to complete the circuit. That's what they call it, earth ground. So in order to do that, whoever builds your house takes all the ground lines and neutral lines from your circuitry, runs them into one cable, and buries a conductor deep in the ground, like 20 feet down. So it has access to moisture. In other words, that you complete the circuit. If it's in dry soil, it's not very efficient. So they go really deep to get into the groundwater. So that's how you complete your circuit. And this is the way we complete the circuit in our battery is we connect the two solutions with an external wire and an external salt bridge is one way, which is made up of ions. And we'll talk about that in just a minute. Or you can have a porous disc between the two. You don't want wholesale mixture of one side with the other. So a porous disc works very well. It's very efficient because there's a very short distance that the ions have to move. You know, salt bridge, there's more internal resistance, we say. Every battery has what we call internal resistance. So we can calculate the theoretical voltage for a battery, but it'll always be practically less than that. All right. We complete the circuit with that salt bridge, say, but there's another reason for that. The other reason is that in chemistry, we don't have any unbalanced charges, right? Only physics has static electricity. In chemistry, we want to balance all the charges. So in order to do that with the salt bridge, we allow ions, if we're pumping electrons into this side, right? We're going here, we're going this side, and we're pumping electrons in this side. That means this is gaining excess electrons, electric charge. We're moving them from this side, so if we let it go like that and only allow the electrons to move, well, actually, theoretically, we build up an excess charge. But if we do this and we have a salt bridge, then we can allow positive ions to move out here and balance those negatives, and negative ions to move out here and balance those positives. So that's the other reason we do it. Yeah, the salt bridge usually contains a strong electrolyte in a gel matrix. Either that, or it could be liquid with a gel plug at the end. Some plug to keep things from mixing wholesale. We don't want that. So this is where we access the electrons in their movement. And that allows us to gain access to energy, right? And we can light my flashlight with a battery. Okay. Terminology. Typically, the way this diagram is written, we put the reduction step on this side. So this is where reduction occurs at that electrode. And on this side, this is where oxidation occurs. Sometimes the electrode is a participant in the reaction. Sometimes it's not. But this is always true. The site of oxidation is at the electrode. The site of reduction is at the electrode, because that's where the electrons are leaving or entering. Okay. And we have a name for it. This side is the cathode. This side is the anode. And it's always the case, the cathode is the site of reduction. And the anode is the site of oxidation. That means that this side has the reducing agent, this side has the oxidizing agent. Just to complicate things further. And usually, sometimes an author will get confused. But usually, we put the cathode on the right and the anode on the left when we draw these diagrams. All right. What do we mean by cell potential? And usually, if we have access to script, we write it in a script E, or we just say this, and that's the cell potential. That is, what's the voltage in that line? In other words, what's the push? How strong is the push of electrons through that conductor? We measure that with a voltmeter. Okay. Well, you could think of it as a pull, or I think of it as a push. I don't like pull very much. Einstein didn't like it either. So pushing electrons that direction, how strong is that force? The electromotive force, the EMF, is measured as a cell potential, and the unit of measure is the volt. Let's see, did I put that down here? Yeah, there's the volt. Unit of electrical potential is the volt. How strong is that push? So I remember in high school, we had some stupid kids who decided they were going to climb a tower where there was high tension lines going through it. I don't know how strong they were. I don't think in that area they were in, they were the really high ones, like 1.5 million. They were probably 100,000 volts. And they got up in the tower, and as long as they didn't touch the wires, they were fine. You might feel a little tingle. But one of them started to fall, and he grabbed the wire. And his foot was still on the tower. And he got a shock, fell to the ground. He lived, but he wasn't the same afterwards. Now, if it had been, and we use alternating current in this country for everything, transmission and service. That means that it goes positive voltage, and then it goes back negative, positive and negative, 60 cycles a second. In Europe, this is 120 volts AC. In Europe, they use 230 or 240, 50 hertz. But a lot of the transmission lines are now being converted over to direct current. When the transmission of power, which was the brainchild of Nikola Tesla, and his benefactor was Westinghouse, the technology was available to convert low voltage to high voltage using alternating current because of fluctuating magnetic field, and we won't go into those details. But now we have the electronics, the systems that are able to boost direct current up to very high voltages. And there are advantages to that, which I won't go into. But if that kid had grabbed a direct current line, he would be dead. Because in an alternating, have you ever touched a bare wire before by accident? It feels like a hum in your body. That's because the voltage is going this way, and then for a period of time, it's zero. And then it goes the other direction. So that zero, if you're quick enough, that zero allows you to detach. Whereas direct current, once you start, you're stuck. Okay, back to batteries. Voltage is a measure of push. Most batteries and most galvanic cells are, by comparison, low voltage. Right? 1.5 volts in most dry cells, C, D, AA, AAA cells are 1.5 volts. You can stack the cells together, like if you have a cell here, here, here. And let's say you're in your car battery, which is a lead acid battery. And each one of those cells, you'll see, you would see 6 caps on top of your battery for each cell. You have 6. And if you run them in series like this, so this is the plus side and this is the negative side, and you connect them like that, right? And you just keep going down, then the total is 6 times 2 equals 12 volts. That's how you get a 12-volt battery. If you put the cells in series, then they add up, their pushes add. And for some diesel engines, they'll put 12 together and make a 24-volt. Okay, what does the volt mean? In algebraic terms, the volt is 1 joule of work per coulomb of charge transferred. So 1 volt equals 1 joule of work for each coulomb of charge. And coulomb is a value that was grandfathered in. It was developed as a unit of charge, and it has its origins. We won't go into that. And we know what a joule is. So 1 volt is equal to a joule coulomb. What we have to do if we're going to use chemistry, we don't talk in terms of coulombs in chemical reactions. We talk in terms of moles of electrons. So we need a conversion factor to go from coulombs of charge to numbers of electrons. And we got that. Let's see. Well, it's coming. Let's see. Let's start this.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The 2 solutions are connected by a porous sodium chloride salt bridge that prevents the 2 solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay. There we go. Okay, so if the electrode participates in the reaction and it undergoes oxidation, then the zinc metal atoms become zinc ions and move into solution, that means the mass of that electrode decreases. And for the flip side of that coin is on this side, the copper electrode increases in mass because we're reducing copper ions to copper metal and depositing on that electrode. The narrator mentioned activity. Since zinc is more active than copper, if you were chemistry majors, you would have to memorize a series of metals according to their activity. And the more active would be up here and the less active would be down here, so that you could just say, pluck, pluck, right? I know that this one is more active than this one. This one's going to be on the anode side. This one's going to be on the cathode side. It just makes things quicker. But since you're not chemistry majors, we're not going to do that. But just so that you understand the concept of activity, this one is more likely to be oxidized, and this one's more likely to be reduced in combination with that one. Okay, how do we measure that cell potential? Right, we've got a device up here that measures it. Well, the cheapest way is with a voltmeter, or you can go to any store and buy for just a few dollars a multimeter, which does voltmeter and it does other things. It measures amps. It has a circuit tester in it with a buzzer that sounds if you've got a complete circuit, and some other things. But the part of that multimeter we're focused on here is the voltmeter part. The voltmeter, the way it measures voltage through that line is it uses Ohm's law, if I can remember how to write it. Let's see. I think it's B equals R. Actually, the way Ohm's first wrote it was he put R on this side and he had volts over I. I is current. This is volts, right? This is volts. This is current in amps. And an amp is equal to, 1 amp is equal to, and the symbol is A. Actually, the abbreviation for the unit of measure is A. 1 amp equals 1 coulomb per second in a conductor. So if we fix our gaze at this point, if it's a 1 amp moving through that conductor, then it's 1 coulomb passing that point every second. Okay. And what a voltmeter does is it has a known resistance, right? This is a constant built into the instrument. And then it measures the current. It measures the current and uses this equation. If it can measure the current and we know what the resistance is, then we can solve for the volts. And it does that, electronically. The problem with that is electrons have to be moving in order to make the measurement. And since they're moving, they encounter resistance in the conductor plus resistance in the voltmeter. So the value that you get in the very good voltmeters, they do an internal correction for that loss. For the voltmeter, they can't do a correction for the wire. So your values are not as accurate. Right? If you're depending upon 3 decimal points of voltage measurements, then we need another device. And that's called, maximum cell potential can only be measured under conditions where there is no current. And that means voltmeter can't be used. If there's no current, then we can't measure it. Right. So what we need is something called a potentiometer. The potentiometer is placed here where the voltmeter would be. And what the potentiometer does is it has built into it a a galvanic cell that applies a voltage in the opposite direction. So, and we've calibrated it so that we know what that voltage is, and we adjust the voltage in the reverse direction until we get no current. So we're at zero current. That means we're at maximum cell potential, and that will give us, the potentiometer will give us a very accurate measure of the maximum cell potential. But potentiometers are very expensive, and they have to be periodically calibrated. So research labs are typically the only ones who use them, or companies that do research. Okay, so here's our digital voltmeter, and we notice that we do have a complete circuit all the way around. Now, what do we mean by standard reduction potential? What we're doing is we're setting ourselves up for producing a table of voltages for different reactions, so that we can calculate proposed reactions. We can go to this table, and it will help us determine what to expect from a reaction that we haven't done yet. So we start off with standard reduction potentials. And when we say reduction, that means we have some ion here. It doesn't have to be a metal, but as an example. That means the electrons are always on the reactant side, and they produce something over here like that. So that, and then we measure the voltage for that process. Okay. But in order to be standard, we have to have 1 molar solution here, 1 molar solution here. And if there are any gases involved, the gases have to be at 1 atmosphere pressure. Yeah, and we can measure the standard reduction potential. Now, this in and of itself cannot be measured, right? Because if those electrons are being added here, they got to come from someplace. So we have to have another reaction coupled to that in order to measure that. And so we have standardized these measurements against an electrode, and that's called the hydrogen electrode, standard hydrogen electrode. Compared to what? We can't measure the voltage unless we have a standard hydrogen electrode. So if we put zinc in this side, and on this side, instead of copper, we have a tube, and hydrogen gas is being pumped in there at 1 atmosphere. Okay. So it's just barely, it's just sitting right there. The gas is sitting right here. Especially if it's submerged in a liquid, the pressure outside is a little bit more than the pressure inside. So you might even see some liquid go up into the electrode, but the standard pressure is 1 atmosphere. Okay. And this is a conducting electrode. It has to be in order to make the circuit. And we compare that voltage against this one. Since this one's 0, then whatever we get on this one is the value of that reaction. So when we set it up in a table, we'll have the standard hydrogen electrode somewhere in that table, and it will always be 0 volts. And then you will have, I can't remember whether it's positive first or negative first. Okay, we're coming up. Oh, and temperature. I forgot temperature. 25 degrees. That's standard temperature for everything except our gas laws. Remember, standard temperature for gas laws is 0 degrees. Okay. So, every member of that table is written as a reduction. But if in comparing reactions, if we have two reactions that we want to put together, and one of them has to be flipped, of course, if they're both reductions, we're not going to get a reaction. So one of them has to be flipped into an oxidation. We're going to talk about that in a minute. But when you do that, that means the standard potential for the cell that was flipped has to change the sign. Okay, just goes the other direction. If we have to multiply by an integer, when we combine two equations, the standard potential does not change. Standard potential stays the same no matter what you do to the equation. Why? Well, I put it in parentheses because it's an intensive property. It doesn't matter how much you have. So the galvanic cell will run spontaneously in the direction that gives a positive electrical potential. Right? So we want to position one of the reduction. We want this one to be an oxidation. So this one will be the flipped equation. This one will be the reduction equation. And if we combine the two potentials from these two and it's positive, that means electrons will flow spontaneously that direction. If we think we've got a cathode and anode and we put them together and it goes the other direction, that means we flip the wrong one. And it'll give us a negative voltage that direction, but a positive voltage this direction. Proof to come later. We're gonna combine some of the chapter 17 into 18, talking about spontaneous reactions. Okay, this is only part of the table that's in your textbook. It starts with the very largest reduction potential for fluorine, difluorine. Difluorine plus 2 electrons yields 2 fluoride ions, and it has measured against a standard hydrogen electrode, has a plus 2.87 volts. And they get smaller and smaller as we go down. And I think I've got more on the next one. Yeah. Let's see. There's copper at 0.52. So zinc must be up in that previous one. Where's zinc? You know, maybe it's the other way around. Oh, that's only copper 1. Ours was copper 2, wasn't it? Yeah, ours was copper 2. So zinc should be, well, where's zinc? Did I miss it? There's copper at 0.34 volts against the hydrogen electrode. There's the hydrogen electrode at 0. There's zinc. Oh, okay. So these are reduction potentials. And that means zinc needs to be oxidized. So zinc would be plus 0.76 on this side. And copper would be, what did I say? Copper would be 0.16. So plus 0.76 and a plus 0.16 gives you a positive voltage when you combine them. We're going to use this table in a minute. I just wanted to show you this, the arrangements of the tables. They're all reduction potential half reactions. Okay. So once you've decided which one's the cathode and which one's the anode, then all you have to do is add their voltages together. Right? This one's going to be as written reduction potential. This one's going to be flipped. And when you add them, if you subtract the anode from the cathode, then you get the potential. And that works. That works. It's fine if you want to do it that way. The way I do it is I look at the reduction potential for the two reactions. Let's go back and do that, unless I have it. Is it in my slide? No. I want to do it for copper and zinc. So let's see, it's not there. There's copper. Copper 2 plus is 0.16 volts. So copper 2 plus 2 electrons yields copper, right? And that's 0.16 volts, 0.16 volts. And then if we write zinc, 2 plus 2 electrons yields zinc, then its value is up. It's up here, isn't it? No, I missed it. Where is it? There it is. Minus 0.76. Minus 0.76 volts. These are both written as reduction potentials. Okay? So if we want to be sure that we've arranged them in such a way that they give us a positive voltage, then which one needs to be flipped when we add these together? That one. If you flip that one, you get a negative voltage. You flip this one, right? If you do this, then you get 0.92 volts. Standard potential. That tells me that this one has to be the anode and this one has to be the cathode. That works so much easier for me when I do it that way, rather than rely on that equation. Okay. Let's see. Okay, here we have an example. Iron 3 plus going to iron 2 plus, and copper metal going to copper 2 plus. If we separate these into half reactions, then the iron 3 plus is reduced to 2 plus. That means it's reduced. For now, we're putting it on the cathode side. And if we take the copper and we write the copper with the copper on the wrong side, it's 0.34, right? But if copper needs to be the oxidation on the anode side, then we need to flip it. That makes the value negative. Add them together, and that gives you the voltage for the cell if the copper is anode and the iron is cathode. There we go. 0.77 volts. Now, one other thing you'll notice is the copper side, right? The copper electrode participates in the reaction. But on the iron side, right, they're both in solution. So what we need is an inert conductor here. The reaction still takes place at the conductor, but because the reaction is completely aqueous, then the reaction takes place at the conductor, but the conductor doesn't participate. It only provides electrons. So if you got money, we can make it out of platinum because it's inert. But if you don't have a lot of money, we usually make it out of carbon, graphite electrodes. Okay. All right, that's one example. So there's our cell reaction for the cathode. There's the anode. And there's the balanced equation with a cell potential of 0.43 volts. Now that's standard potential. That assumes that this solution is 1 molar, 25 degrees Celsius. And since there are no gases, we don't have to worry about the pressure. But most cells are not built that way. They're not built standard. So we need a way to find out the actual voltage based upon the concentrations in solution and upon the electrons that are moving. And right, we have to consider the quantitative transfer of electrons to calculate the actual voltage. That's where we need, in our balancing steps, we had like 2 moles of electrons or 6 moles or 10 moles of electrons. That we need to remember that number in order to use this equation, the Nernst equation. Believe that's some guy's name, Nernst. He probably got teased at school. All right, that's coming in a minute. And let me clear this out. It's getting kind of busy up here. Do it 10:30. I don't know how useful these slides are going to be. Order the following from strongest to weakest oxidizing agent. In order to determine oxidizing agent strength, we need to look at what's the voltage of reduction, because the strongest oxidizing agent will be the one with the highest reduction voltage. All right, most easily reduced will be the highest reduction voltage. So we don't know values for some of these elements. That's a problem. If we take what we do know, fluorine reduced, sodium, well, we're comparing iron, sodium metal, fluoride ion, sodium ion, and chlorine. Then we write them as reduction because we're looking for the highest voltage of reduction to order them for oxidizing agent. So we're going to write them as F2 plus 2 minus yields 2F minus. Sodium plus an ion is sodium. Chlorine plus 2 ions is 2 chlorides. And Fe3 plus 3 electrons is Fe. Let's see. All right, so we've written them. All right. So if we're comparing these guys up here, this one is on which side? It's on that side. So it's backwards. This one is on that side, so it's backwards. This one is on the wrong side. This one's on the correct side. And this one's on the correct side. So these two have to be flipped. Okay. All right, we don't know the voltage of that one. It doesn't make any sense, right? Because sodium doesn't want electrons. It's a metal. So it's not likely to be reduced. Right? It's going to resist reduction, just as iron is going to resist reduction. That's why those question marks are in there. Right? We do have those values. So we're going to say that sodium and iron are on the way bottom end, right? Even if we consider them as valid oxidizing agents. And then fluoride, of course, is not going to be good either. Right, those others don't have standard reduction potentials to speak of to compare their values. The remaining F minus sodium and iron shouldn't be easily reduced. In other words, what we're saying is that the dichlorine is probably the strongest oxidizing agent. All right. Shorthand. Remember, we had the anode on this side and the cathode on this side. We can write that rather than drawing that picture. We can write it in shorthand, line notation, we call it. Right. The anode's going to be on the left, cathode's going to be on the right. We separate the two by a double vertical line. So that's where we start. That just means that cathode over here, anode over there. Okay. And we try to sort of mimic the physical arrangement of things. So we put a vertical line in anywhere that there is a phase change. Right? So if we have a vertical line here and a vertical line here for our zinc copper galvanic cell, copper was on the right hand side, right? So here's the copper electrode right there on that side. And then we have the copper 2+ in aqueous solution here. Then we have a salt bridge or a porous disc here. Then on this side, we have zinc 2+ in aqueous solution. And we have the zinc electrode on this side. And that's to mimic the cell because we would connect this electrode with that electrode. Okay. That's just the basics of line notation. If we have, if we know the concentrations of these things, then we write that in also. Right? If it's a standard cell, we don't write anything in, we just assume it's 1 molar. So here's another example where we have magnesium as an electrode in the anode and aluminum as a cathode electrode. And then we have 3+ aluminum and 2+ manganese in solutions. Here we go. We should be able to reconstruct the reaction based upon that line notation. If we have an inert conductor, like, here we go, for this reaction. We have silver electrode and we have, well, let's see which one's which. Let's do that first. Let's analyze this thing logically. Right. If we have the silver plus an electron yields silver solid, and then we have reduction potential for 3+ plus electron yields Fe2+, and it's aqueous, and aqueous. Okay, and the voltages are 0.80 volts, and this is 0.77 volts. So which one needs to be flipped in order to give us a positive value? Do this one. If we make this one negative, then that one reverses. This becomes the anode, and this is the cathode. Okay, and we should get a standard potential of 0.03 volts. Not very much. Okay. Okay, that's how far we've gotten. Then if we combine these, then we would put this one over here along with silver. And this one would be silver solid plus Fe3+. And that would be the overall chemical reaction. If we needed to do some calculations like if we need to determine Q, for instance, or K. We would need this one in order to do that calculation. We couldn't do it with separates. We have to have the overall equation. And let's see. Yeah, that's balanced. So how many electrons are actually flowing here? Well, one electron, right? Just 1 mole. So there's 1 mole of electrons that is changing places. Come on. That's true. That's true. Here we go. Right. Cathode, anode. There's the picture view. And we're using a platinum electrode for the anode in this case. Now, a porous disc makes things a lot simpler. If we were to use a salt bridge and put a salt bridge over there, what could we put in the salt bridge as an ionic solution? What should we not put in that salt bridge? Chloride should be nowhere near that galvanic cell. Because if the chloride moves into the silver side, it's going to precipitate. And that's a conflicting reaction. So we would put something like potassium nitrate or, I don't know, something where we wouldn't precipitate. Nitrate would be good. Potassium nitrate would be a good example. Okay. How about line notation? Well, if we're going to have this as the cathode, that means we have our porous disc or our salt bridge, and we're going to have cathode here, it's silver on this side, and silver ions here. And then on this side, we would have what? Well, we would have, flip it, and then we would have, we're oxidizing Fe2. So we're oxidizing this one to this one. And then electrons are being transferred like that. Oh, we need the platinum electrode in there also. So we just put I don't know. If it's a phase change, we would need that, wouldn't we? Oh, and that would not be right because the line means difference in phases. There we go. That's the way it should be. So platinum is a different phase. It's a solid, and these are in aqueous solution. This one is the one that's being oxidized to that one. This one is the one that's being reduced to that. Okay. Let's see. All right, this is just a review. We have our composite reaction. That tells us several things. It allows us to calculate K or Q, and if once we balanced it, we know how many moles of electrons are being transferred. All right, here's an example where we want to sketch a cell using the following solutions. Copper and silver, right? Which one would be the anode? Which one would be the cathode? Well, the standard reduction potential for copper is 0.34. Standard reduction potential for silver is 0.8. So we have to flip the copper and make it the anode. That's why copper is on the anode side, silver is on the cathode side. And we get an overall voltage of about 0.5 volt under standard conditions. All right. So what would happen to the potential if we increase the copper concentration? Let's write the entire equation out. I think that would be more useful. We're going to invoke Le Chatelier here. So if the anode is copper going to copper 2 plus, goes to copper 2 plus, and the cathode, and by that we have, excuse me, yeah, 2 electrons. And then we're going from silver to silver metal. Then we would have to multiply this by 2, 2, and 2 to balance those electrons. Notice we don't have oxygen or hydrogen in this one. Then we could bring them down. So copper solid plus 2 silvers yields copper 2 plus 2 silver solid. Would be the overall equation. Okay. What would happen if we increase the copper 2 plus concentration? If we increase this, it's going to drive the reaction back this way, right? Which would be an opposing reaction, right? If we drive this one back that way, then this one has to be driven back that way also. So what we're doing is we're actually decreasing the cell potential. If we have a standard potential going this way and we're pushing backwards against it, we're decreasing the potential. Okay. Okay, we're going to try to equate, and how much work can we get out of the galvanic cell? Well, the problem is, if the cell is spontaneous, we've said that E is positive. When we say spontaneous reaction, that's how we're going to get any kind of work out of our movement of electrons. So E would have to be positive. But if we're going to get work out of the system, it has to be a negative value, doesn't it? Because system and surroundings, if we're taking work out of the system, leaving the system, it has to be negative. So we've got a sign conflict there. All right. So we end up with cell potential. Let's see, cell potential equals is, actually, let's do it this way. Cell potential is proportional to work per Q. Q, in this case, Q is charge. When we were doing thermochemistry, Q was heat. But in this case, it's charge in coulombs. So remember, joules per coulomb. That's the definition of voltage. Right? But they're proportional, but we have to take account of the signs. So if this sign is negative, we got to make it a positive. So that's why now we can say they're equal as long as we do that sign change. So if we solve for work, then work is going to be E times Q, negative E times Q, or negative W equals QE. Now that's the maximum amount of work that we can get. Of course, we're never going to get that much. All right. Oh, there's the explanation. Units of measure. Joules per coulomb is volts. So that's why W over Q works. Come on. There we go. So if we say, now, the units have to be in volts and coulombs in order to give you value of joules. Okay, in any real spontaneous process, some energy is always wasted. So the actual work is going to be less than the calculated maximum. Let's see. All right, here's our conversion factor. It's called the Faraday. And it's named after a brilliant experimental scientist, Englishman. He never got a college degree, but because of his work, he was eventually inducted into the Royal Society. So Faraday is units of moles of electrons or coulombs per mole of electrons, 96,485. So 1 Faraday equals 96,485 coulombs per mole of electrons transferred. That's the Faraday. That's our conversion unit, so that we can do stoichiometry with in conjunction with electrochemistry. Okay. We can also speak of this in terms of free energy. In other words, the free energy, the maximum amount of free energy available from a process is the maximum work that can be done. So any change in free energy is also equal to that value of work. If that being the case, then we can set this change in free energy equal to work, maximum work. I shouldn't say change, say maximum work done. So change in free energy equals minus EQ also. Okay, so what about the charge? Well, if we say this is in terms of Faraday units, this is in terms of charge, right? This is charge, and this is moles of electrons. Then we can say that Q, coulombs of charge, equals Faraday's times the number of moles of electrons moved. Then we can substitute that into this Q. And if we do that, then that equals to negative E Faraday. There he is, Michael Faraday. Okay, so this free energy that can do work for us is proportional to the difference between the free energy of the reactants and the products. So we want positive cell voltage, which means we want, and remember, a spontaneous reaction is a negative delta G. That makes for a spontaneous reaction. And that produces a battery. Now, let's see, I'm gonna leave that there. Let's put this delta G equals, how did they write it? Minus NFE max. Okay. Leave that there. Notice anything funky about this cell? It's got the same reaction on both sides. It's known as a concentration cell. The difference is one cell has a low concentration and the other cell has a high concentration. If you do that, you can produce a voltage. It's a very small voltage, usually measured in millivolts. But in this case, we have the reaction is silver ions going to silver metal. And notice that if we have on the low concentration side, the reaction is going to be favorable towards producing more ions because they're low. On the high side, we've got too many ions, and we're going to deposit those on the electrode. Okay, we have the same electrodes, but we have different concentrations. That's required. The lower concentration will increase, the higher concentration will decrease. They're trending toward equilibrium. And in order to do that, we need equal concentrations on both sides. And that will happen as long as you've got enough silver on the low concentration side to be consumed. If you don't, then it'll be all chewed up and the reaction will stop anyway, but it won't be at equilibrium. All right. Oh, here's Walter Hermann Nernst. He was German, so his name probably wasn't that unusual. He worked in the area, let's see, this was at the end of the 19th, beginning of the 20th century. So there was a lot of activity in thermodynamics here and physical chemistry. And so he used what he learned there to enhance his understanding of electrochemistry. And he was also working on solid state physics because we're in the first part of the 20th century. Solid state physics was becoming not just popular, but essential for modern technology. And that's in terms of like electronics. That's all solid state. So he came up with this with a theory of heat, and that led to the expression of the third law of thermodynamics. And for that, he won the Nobel Prize. And this Nernst equation, I don't know if it was an afterthought or just a mathematical extraction from some of his other work, but it's very useful. He came up with that one actually early in his career. Right, he was in his 20s. I assume those were his birth dates, birth and death. So in his early 20s, he came up with this Nernst equation. All right, well, there's the third law. We covered that already in the previous chapter. All right, so here it is in its raw form. The actual cell potential is based upon the standard cell potential, and then it's adjusted by these factors, right? Standard, the gas constant, temperature, number of moles transferred, the conversion factor, and the natural log of Q for the reaction. Now, again, if you were chemistry majors, you'd be working from this one. But since you're not, we're going to use a revised version that is more useful for us if we fix the temperature at standard. And we incorporate the Faraday constant, the gas constant, standard temperature, this one, combine those all together, plus convert this one into natural log. I mean, not standard logarithm. Not base E, but base 10. Okay, if we do all of those, then we come up with a modified equation that's much more useful. And there's the math. And what we end up with is this equation. We still start with the standard potential, but now we subtract 0.0591 over moles of electrons times the base 10 log of Q. This is the one we're going to use. Oh, you don't have to know that. I just wanted to prove to you that the conversion of natural log to common log is that factor, 2.3026. Okay. So if we're at 25 degrees and equilibrium, Q equals K, then if Q equals K, then this is K. And let's see. Here we go. Here's the explanation. If Q equals K, well, we intuitively know that the system is at equilibrium. That means you're not going to get any voltage out of it. That if you have, if Q equals K under the hood of your car, you got a dead battery. So, okay. Actually, it's just a statement of fact. If Q equals K, then E equals 0. Well, if E equals 0, then that means that this is not log of Q anymore. This is log of K. So if this is 0, that's K. And then we can solve for E0. And it gives us another way of measuring K for a reaction, or determining what the standard potential is for the reaction. If we know what the equilibrium constant is for a reaction, then we can calculate the standard potential for that reaction, or vice versa. Okay. Here we have S4062 minus, chromium 2 plus yields chromium 3 plus, and S2032 minus. These are the half reactions. So which one has to be flipped? Well, I would flip the bottom one. I would flip the chromium. And that would give us a positive voltage. So the chromium is going to be the anode, and the sulfur is going to be the cathode. Reverse reaction 2, multiplied by 2 and added to reaction 1. Then we get this overall reaction. That's the cell reaction, and there's the standard voltage. 2 moles of electrons are transferred for every unit of reaction. Let's see. N equals 2. So if we say okay, so what we've done, before we had E0 equals 0.0591 over N log K, right? Yeah. So to solve this one, we've just moved this one over here and that one over there. Actually, it's more complicated than that. If we want to solve for K, we have log K equals, and then keep this one here and flip this one over here. E0 times N over 0.0591. Then we've calculated E0. We know the number of electrons, the moles of electrons moved, and we can calculate K. K is 22.6. All right. The significance of that is K is massively high. That means the equilibrium is way, way to the right for that equation that we had on the previous page. So way to the right. It's headed for 3 plus chromium and S2032 minus. right? So that means since this is the cathode, it's headed toward this one, and it's using up these. Excuse me, no, it's using up these, CR2. So it's way favored to the right. That tells us that equilibrium is to the right. And E0 at 0.67 tells us also that equilibrium is to the right. It's spontaneous in that direction. So there's two lines of evidence for the reaction proceeding as written, left to right, spontaneously. Oh, excuse me. We aren't finished. That's just log K, 22.6. Okay, so K is 10 to the 22.6, which is 4 times 10 to the 22nd. So I was right. I just didn't finish the discussion. K is huge. So the equilibrium is favored. It essentially goes to completion. As long as there are enough reactants, it will run to completion. And this is typical for redox reactions. Once you set them up in the positive E direction, then the Ks are going to be massively large. So when is E? This is just a concept check. E is 0 when the cell is at equilibrium, dead battery. When is E0 equal to 0? For a concentration cell. E0, why? Because in that galvanic cell, under standard conditions, you've got the same concentration on both sides. So E0 has to be 0. But it's not, the actual E is not 0 because we changed concentrations. All right. A concentration cell is constructed using 2 nickel electrodes. One concentration is 1 molar, that's going to be the cathode, and 10 to the minus 4th molar, that's going to be the anode. So we write them that way, cathode, anode. And notice I've subscripted the C and A to differentiate between cathode ions and anode ions and metals. That way, when we put them in the combined equation, we know which is which. So, once we've got this equation laid out, and we know that solids are not part of the calculation, then we put the anode on top and the cathode on the bottom, because the anode 2+ is on the right and the cathode 2+ are on the left. So that's why it's log A over C. Okay. Once we do that calculation, so the anode is going to be 10 to the minus 4th over 1. And we take the log of that and multiply it times 0.0591 divided by 2, because there are 2 moles of electrons, and change the sign. So we end up with a calculated voltage of 0.118 or 118 millivolts for that cell. Now, the best way to decrease the voltage would be to increase the concentration of the anode side. If we wanted to increase the voltage, we would decrease the anode and increase the cathode. Okay, let's see. We have a galvanic cell made with a nickel electrode at 1 molar and silver electrode at 1 molar, and they have, we have to have appropriate solutions. And this would be the line drawing. We look at the potentials, we say, all right, which one has to be the anode? Which one has to be flipped in order to keep it positive? That would be the nickel. So the nickel will be the anode. It's on the left. And the silver will be on the right. This is what it would look like if we drew it all out. And I'm using sodium nitrate as the salt bridge simply because of silver. We can't mess with chlorides when we're dealing with silver. Okay. So there's the standard potential, right? We flip the nickel and we've got a 1-volt cell with silver and nickel. All right, we talked about lead acid batteries before. Up to this point, we've only discussed galvanic cells that required either a salt bridge or a porous disc to separate them. And the reason we did that was because the solutions could not mix, right? But what if the solution is the same in both cathode cell and anode cell? In this case, the solution is sulfuric acid. It's the same for both of them. So we don't need salt bridge. We can just suspend everybody in the same solution. And that's what we've done here, right? The anode is made of lead. So lead's going to be converted to lead 2+. And the cathode is lead 4 oxide, PbO2. And that lead is going to go into solution as lead 2+. So we're adding the same ions from both electrodes into the solution and consuming the sulfate in the process. Let's see. Here's the overall reaction. Right. There's the lead electrode, there's the PbO2, there's sulfuric acid. We're going to end up with PbSO4 and water. So there's no need for a salt bridge or a porous membrane to separate the cells. And that makes for a more compact cell, easier to maintain. And it used to be, in the olden days, when you had full service gas stations, that while your tank was being filled, the technician would pop your hood and pull out some of the battery fluid into this device called a hydrometer, and it checks the density. It's the density of the full strength sulfuric acid is a certain value, and this hydrometer is calibrated. So if your battery is being discharged too far, then it'll go into the yellow or the red, and you can tell how much life is left in your battery. And if it needs fluid, instead of adding water, they add sulfuric acid. Okay, right. When the battery is fully discharged, both the anode and cathode are converted to lead sulfate. Now that can happen. You can have both electrodes turned into lead sulfate because that's the product for both reactions, both half reactions, produce lead sulfate, lead 2 sulfate. That can happen on older batteries, especially on the surface of the electrode, right? It's a solid. So it's deposited on the surface of the electrode. And then when you run your alternator, it charges the battery, it runs that reaction in reverse and consumes the lead sulfate and produces lead on one electrode and lead 4 oxide on the other one. As long as the electrons can get through that crust of lead sulfate on the surface, and usually they can, unless it's really, really gone too far. And then we say your battery is sulfated out because the crust is impervious. Electrons can't move and the solution can't interact, so your battery is dead and unrecoverable. So at that point, you just get a new battery and let the recycling factory take care of it. But with modern batteries, the construction of those plates is such that this rarely ever happens. Right? They have a much higher amperage because of the surface area. on the plates, and with that surface area and the construction of the plates, you very rarely get sulfated batteries. This is a dry cell. Notice that the anode is the casing. Right? The outside of the battery that you see is a polymer film. Right? Underneath there is the zinc casing. That's the anode. And in solution, the reaction takes place with manganese dioxide and ammonium chloride. And the cathode is that carbon rod, right? Because it doesn't participate in the reaction. And that's why when you see batteries stacked in a package, you always have the nipples pointing in the same direction. Right? Because if they're pointing in the opposite direction, then you're more likely to get bleed over and deteriorate the battery over time. And that's why when I take batteries out of a package and I want to store them, I carry them around with me, I'll be sure that they're stacked that way. And then in my Ziploc bag, I tighten them up and put a rubber band around them to hold them that way so that they don't touch the wrong electrodes. Okay, I already mentioned that. This is a mercury battery. We don't use these anymore because of obvious reasons. But batteries like this, like you'll find in the calculators and in hearing aids, small devices, these batteries lend themselves to small form with high voltage. And the substitute, I don't know if I have the substitute here. No, I don't. Substitute, instead of using mercury, I think they use silver. Yeah, silver is a substitute. This is kind of like a battery. It's a fuel cell. It's a battery in the way that the spontaneous reaction of hydrogen and oxygen gives you a voltage, the spontaneous voltage, and it produces a product of steam, just produces water. But the advantage is that your electrolytes and your reactants never run out as long as you've got a supply coming in. So this was the technology that was used in the original space program. The Mercury, the Gemini, and Apollo spacecraft used fuel cells. They were more developed for the Apollo because we were going farther and farther away from the sun, and solar cells would have been cumbersome. So they just went to fuel cells. One of the disadvantages of fuel cells of that older vintage is they operate at very, very high temperature. They have to operate at high temperature to react. So that's a problem in transitioning to a common usage in, say, automobiles. The other disadvantage is how are you going to store those gases? Oxygen probably wouldn't be such a problem except if it were pressurized. You know, pressurized tanks can be hazardous. The hydrogen, you pressurize hydrogen into a tank and all you need is a small leak and you've got an explosion. So they've been working on that type of problem. The hydrogen economy, they say, is like the holy grail. The holy grail power generation is fusion. But if you've got cheap source of energy, you can split the water molecule into hydrogen and oxygen, and then that can go into the infrastructure, which is another problem for hydrogen vehicles. We can't run hydrogen vehicles widespread across the US now because we don't have the infrastructure for it. It's all based upon fossil fuels. And it would be a massive investment to do that. So if you get one of these vehicles, and they're only experimental now, if you get one and try to run across the country, you've got to carry all your fuel from one side to the other. Okay, so let's talk about corrosion. Corrosion is the term for degradation of a metal using a redox procedure, a redox reaction. And it's usually undesirable. Corrosion has a negative connotation. Metals in the environment, most metals are found in compounds. Like Fe2O3 in iron ore is where we get iron for smelting. Al2O3 is bauxite, where we get aluminum. And those are the natural states. They want to be in compounds. But in order for us to use them, they need to be metallic. So once we get them into that metallic form by smelting, usually of some form or another, then all we need is some oxidizing agent. Yeah, oxidizing agent to come along, and we get corrosion. So iron turns to rust. Aluminum is kind of special. Aluminum is a very reactive metal. And the reason that you can take an aluminum can, throw it out there in the yard, and 100 years later, it's still there. The reason for that is aluminum is so reactive, right, that this part of the can, this aluminum, would react with oxygen from the atmosphere, and it forms a continuous impervious layer of aluminum oxide on the layer. Now the oxygen can't get to the aluminum underneath, right? So it's counterintuitive. It's a very reactive metal, but it persists in the environment forever because of that factor. And actually, we use this type of reaction to make stainless steel. Right? If you leave just regular carbon steel out in the environment, like you see an old car, a junker, or a tractor out in the field, and you watch it for several years, eventually it'll just flake into nothing for two reasons. One is, actually the main reason is, iron is relatively reactive too, not as high as aluminum, but it produces rust. But the difference here is that the density of aluminum and aluminum oxide are about the same. So it forms this layer, and there's no push to make it expand. Whereas Fe2O3 has a lower density than iron. So what you'll see is this old tractor, this old automobile out there, the rust will flake away. And what that does is it exposes more iron underneath. And it just continues doing that. As this expands and flakes away, the iron is exposed to fresh oxygen and water, and it just rusts down to nothing. Now, I'll tell you a story. Some smart, thought he was smart, architect. Well, actually, it wasn't the architect's fault. He was using a new type of steel that was supposed to rust as fast as aluminum changed to oxide. Only the density of the aluminum, the iron oxide, was modified somehow so that it would seal the iron underneath. So once it rusted and produced that bright red color, it would just stay there, right? And it wouldn't rust anymore. So some architect got the bright idea to construct a building in Atlanta called the Omni. And the Omni was used for a bunch of things. What I remember was the basketball team, I forget their name. The hockey team, the Atlanta Flames, played there. And it had this nice, bright, white concrete around it, and this building made out of that iron on the surface, coated. So Atlanta gets about 45 inches of rain a year. So it would rust and produce that beautiful red color, and then the rain would hit it, and it would wash off, and you have red streaks running across your white concrete. And eventually, the city fathers, I guess, had enough, and they said, get rid of that thing. So they tore the building down and put something else up. Okay, so we oxidize metal, and that's corrosion. All right, so here's an example of a galvanic cell on the surface of steel or iron of any kind. And with that water droplet, we're producing an anodic area and a cathodic area. But the reaction itself produces rust and consumes the iron. That's corrosion of iron. So question is, iron is such a useful metal in our modern society, right? We build buildings with it, we build bridges with it, we build cars with it, we build everything with it. So what we want to do is protect it or find some way to ameliorate that corrosion. And these are the different ways you can do it. One way that when I was a kid, we used to have a lot of these around, galvanized buckets. Have you ever seen a galvanized bucket? They're not too common anymore. Most often we use plastic buckets. But the galvanized bucket was a steel bucket that was simply dipped in molten zinc. And it produced this beautiful crystalline pattern. Crystal going this way and then that way and then this way and that way. You could always tell a galvanized bucket from that crystal pattern. This is where the reactivity of metals comes in. Zinc is much more reactive than iron. So on the surface of iron, the zinc would react with oxygen and produce zinc oxide and seal the surface. It would sacrifice itself so that the iron underneath, the steel underneath in that bucket would not deteriorate, would not corrode. That's one way, galvanizing. You can still get galvanized nails. Like if you go to a hardware store, you can look in the bin and see galvanized nails, and they'll have that kind of a gray color to them. You can alloy. So that's where stainless steel comes in. So actually, it was a process. Stainless steel originally, and there are a whole host of different grades now, but originally stainless steel was chromium and iron with a little carbon in it, of course. And chromium was about 35% by mass of the total. And we've managed to bring that down some and incorporate other metals in there to modify it and make it more useful. But what happens is, just like that aluminum can, when you scratch stainless steel, you expose the metals underneath, and there's enough chromium in there that it instantly forms chromium oxide and seals the gap. So much so that you may not even be able to tell where the scratch was. That's alloying. And alloying simply is combining two or more elements together, and one of them has to be a metal to be an alloy. Let's see, brass, right? Brass instruments, musical instruments would be copper and zinc of a certain percentage. Bronze, right? Remember the Bronze Age in history, bronze swords and all that stuff. They were made of copper and tin. This is an alloy, but it's not particularly useful for preventing corrosion because the standard electrode potential for copper and zinc are about the same. They're not. Zinc in this case is more reactive than copper, so it tends to protect the copper. That's why it's used on ships where they're exposed to salt water. So alloying is another possibility. Cathodic protection. Cathodic protection has a sacrificial electrode. So let's say we've got a steel pipe right here, predominantly iron, and it's buried in the ground. And if we just leave it like that, eventually it's going to rust. right? Because oxygen will eventually, it'll be slow, but the oxygen will get through and there's plenty of moisture, so it'll eventually rust away. So what we do is we connect a magnesium electrode to that. Or zinc would work also, a more reactive metal. So what this one does is it serves as the anode. And it produces a stream of electrons, right, to this pipe and keeps that iron reduced. This is the cathode. And then, of course, the circuit is completed in the solution. That's the way we used to protect our buried fuel tanks. They were made out of steel. Now they're all made out of fiberglass and plastics. Right, so that's not a problem. We still have some steel pipelines, and those have to be protected. Lots of times what they'll do with steel lines, pipelines now is they'll wrap them in asphalt and polymer something. They usually look kind of green. Okay, so there's your magnesium anode. This technique, let's see, must have some more text out here. Yep. All right. I mentioned coatings. You can paint steel and just you just keep the oxygen away from it. You can alloy it. You can use cathodic protection. Right. So the pipe is the cathode. Site of reduction. Ships, ocean-going vessels. Very often, you may not see it because it might be under the waterline. They'll have a band of zinc wrapped around the ship. And that's a sacrificial anode. So when they're docked and they have to turn the power off to the ship, then the zinc anode is consumed. But they've also got a trickle charger attached to that zinc strip. So as long as it's running, it supplies electrons to the zinc, so it protects the zinc and the ship. So they usually, once you put that zinc wrap on a ship, you don't have to change it. Unless the ship sits in, it's junked, and it sits for a long time in salt water, then eventually it'll corrode away. Okay. Now, we're going to take our galvanic cell and flip it. This process is called electrolysis. That's when you take a spontaneous reaction of a given voltage and you run voltage like we did with our potentiometer. You run voltage backwards, equal to or excess of the forward voltage. That'll run the reaction backwards. So you need an external source in order to accomplish electrolysis. You force a current through a cell to produce a chemical change in the opposite direction, in the negative potential direction. You drive the reaction backwards. Now, this is desirable in several cases. In this case, where the natural tendency is for hydrogen and oxygen to react in a redox reaction to produce water, right? Like in the space shuttle engines. They were hydrogen and oxygen. But we want hydrogen and oxygen separate, right? We want those products. So we put water and we put direct current electrodes in it, and we run the reaction backwards, and out pops hydrogen and oxygen. I used to have a device. I didn't bring it with me because it belonged to the school where I taught once. And it had two tubes, say like this, like that, like that, that. And it had an electrode here and an electrode here. One was positive and one was negative electrodes. And the solution was water with a little bit of acid in it, maybe hydrochloric acid, so just so that it would be conductive. Or you could use acetic acid, it worked. Okay. And the positive would remove electrons. So it would take O, oxygen at 2 minus, and make it O at 0. So oxygen would come up this side, and hydrogen would come up this side. And you could collect them up here, and they had a stopcock there, stuff like that. You could collect them in tubes. And then if you take this one in your tube and you have you ever seen a burning ember? It's a special stick that's treated so that it, once you light it, you blow it out, it still glows. Take the burning ember and put it in there and it pops. That's hydrogen. If you take this one and you put that burning ember in there, it bursts into flames because oxygen supports fire. And the kids used to get a kick out of that. This reaction can occur when we're trying to recharge our lead acid battery in our cars. It's not as much a hazard now because we've got better control systems. So once the battery has reached its full charge, the system senses that it's fully charged and it cuts off the trickle of electrons into it. So it doesn't exceed, because once you got water and your sulfuric acid in there, you can accumulate hydrogen gas in those cells, and just a little spark and your battery will blow up. That's why the older batteries, each one of the caps for the cells had a little pinhole in it for the hydrogen to escape. But now we've got better control, and that's not a problem. We also have sealed lead acid batteries, and they have not just the electronics, but they also have absorbers in there, hydrogen absorbers that will remove hydrogen for you. Okay, so that's one form of electrolysis. Other forms that are commonly used, before I get to that, take metals that are in solution and plate them out on the cathode. It's a way of, especially for copper, it's a special way of purifying copper to 99.999% purity. It needs to be that pure in order to be used in electrical conductors. So copper ore is purified down to maybe 90% or maybe 95%. And then it's sent off to the electrolysis unit, and they dissolve the copper, whatever of copper and all its impurities in a solution. And then they dunk plates in it that serve as the cathodes, and they have a copper matrix. And then all that copper is plated on that, plated out on the plate, and leave the impurities behind. And you pull the plates out, and there you go. Scrape them off, and you got pure copper. Well, in order to do that, in a quantitative nature, we have to know something about the reaction. We have to know the current, how many electrons are being pushed through that solution, because the number of electrons determines the stoichiometry. So we have the current, and how long does it run? That gives you the total number of electrons. Of course, current is in coulombs per second, so we have to apply the Faraday constant to convert the coulombs to electrons before we can do further calculations. Once you know that, then you can determine the quantity of charge in coulombs and then moles of electrons, and then use our stoichiometry to determine the moles of the metal. In this case, our example is copper. The moles of the metal that can be plated out based upon our balanced equation. And then once you know the moles of copper, it's a simple conversion to grams. Okay. So that's just what I just said. So let's see if we can use that sequence of calculations to determine an unknown metal. Say we have an unknown metal that's electrolyzed, and the solution is the metal with 3 nitrates. So we got this metal in solution with 3 nitrates. Each one of these is a minus, so this one has to be a +3, correct? Okay. So we're going to have to add 3 electrons, 3 moles of electrons for each mole of metal to produce our metal solid. And then we don't have to worry about the nitrates because they're spectators. Okay. 52.8 seconds at a current of 2 amps to plate out 0.0719 grams of metal. If we want to find out what that metal is, what do we need? Well, we don't have access to the number of protons. We don't have the atomic number. So we have to go to molar mass. Right? So we've got that mass, 0.0719, 0.0719 grams. Grams per mole. We need the number of moles. That will give us the molecular weight, and then we can go to the periodic table and find out what metal it is. Okay? So what we need to know is how many moles of that metal. Right? So if we go for 52.8 seconds at 2 amps, so 2 amps is 2 coulombs per second for how many seconds? 52.8 seconds. Okay, so that'll give us the number of coulombs. Now we want to convert coulombs to moles of electrons. So the conversion factor is 96/485 for 1. That takes care of coulombs. Now we want to convert moles of electrons to moles of metal. So we use the stoichiometry of our equation. For every 3 moles of electrons, we get 1 mole of metal. That's what we want. How many moles of metal? So if we run that calculation, we'll find out how many moles of metal we've got. That is represented by 0.0719 grams. So I got 2, 52.8, 96/485, and 3. So I've got 3.65 times 10 to the -4 moles of our metal. So I just put that in here. 65 times 10 to the -4 moles. 0.0719. And I get 3 significant figures, 197, right? 197 grams per mole. So we just go to the periodic table and we look for 197. And let's see, 197. Closest I got is gold, right? What is the metal? Okay. Come on. Oh, there it is. So there it is in black and white and blue. Okay. Let's see. Let's remove this. Let's see how we doing on time. Ooh, I'm way over. Good thing we don't have a lab today. What if we have a solution containing 0.1 mole of lead 2+, copper, tin, nickel, and zinc, all 2+ ions? We want to predict the order in which the metals played out as the voltage is turned up from 0. So each one of these metals, we could write it generically like this. 2+ plus 2 electrons yields the metal. So what we want to know is for each one of these metals, what is its reduction potential, right? Since they're all the same concentration, then we can compare standard potentials. We don't have to be concerned about if they were different concentrations, then yeah, maybe we'd have to be more particular. So first of all, do the metals form the cathode of anode? The site of reduction, they're the cathode. And by the way, when we're running an electrolytic cell, if we were to take a galvanic cell, right, with say zinc and copper, and run it backwards, now this side would be the anode because it's the site of oxidation. And this would be the site of reduction. Now it's the cathode. So we swap the names also. All right. The more positive, the standard reduction potential will plate first as the voltage is increased. Let's see, the more positive standard reduction plates first. Well, I want to get the values. Oh, here we go. Here we go. All right. So, notice how would we drive these reactions backwards? If their values are positive, say copper, it's already got a positive value. It wants to go that direction. So it needs the least push to get there. Right? And then the next one is lead is 0.13, negative 0.13. So it would have to, we would have to exceed that voltage at least a positive 0.13 or 0.14 in order to drive it. So as the voltage, the reduction potential decreases, becomes more negative, we need a higher opposing voltage to get that to run in that direction. That's what we're saying. So the order that they were written originally, copper, lead, tin, and nickel, is the order that they would plate out. So we could essentially separate these metals simply by adjusting the voltage and let it run. Let's see, how would you assess when the reaction has extracted all of the metal? Well, you could pull the electrode out and weigh it a couple of times and see if it changed. That'd be the simplest way. There's got to be another measurement that you can make. I bet once you try to apply that voltage, there's going to be an opposing voltage. And when you put the voltage in there that's against the one that's in there, it's going to modify that voltage and the needle's going to move. When it stops moving, then you know you're done with that metal. Oh, I left off zinc, sorry. Zinc is the most reactive, so it's going to take the highest voltage to run that one backwards to make the metal. Okay. Commercial electrolytic processes are absolutely essential to producing the metals that we desire. They can actually produce metal from the ore, or they can purify metals. And I talked about purification of copper. Production of aluminum is another situation. Since aluminum is so reactive, and it has a very, very strong bond with its oxygen atoms, and it takes a lot of energy to break those bonds. So up until modern times, let's see, those are possibilities. Up until modern times, Let's see, did I include that? I didn't include it. I think it was Emperor Napoleon, not the first, Napoleon II of France. So he came later. At that time, aluminum was discovered and it was being produced chemically, but it was so inefficient at producing aluminum that Napoleon II entertained his guests, his royal guests, not with gold or silver utensils, but with aluminum utensils, because everybody knew that aluminum was more expensive than gold. Simply because the process was so efficient, the chemical process. When we get to electrolytic processes, which were developed independently by Hall in the US and Herold in France, the electrolytic processes made aluminum much cheaper. So now we can pull out a sheet of aluminum foil, wrap our food in it, cook it, and throw it away. The trick, of course, these graphite electrodes are necessary because the reaction itself does not consume the the graphite rocks degrade because the electric current is so high, but they don't participate in the reaction. Well, there's a side reaction. Let's put it that way. Notice there's a side reaction. That carbon produces carbon dioxide. So there are reactions in there that consume the carbon electrode, but the one of interest is the one that turns aluminum oxide into aluminum metal. The real trick, though, was reducing the melting point of the ore, aluminum oxide, bauxite. Most bauxite comes from the tropics because those soils down there have been weathered so bad. There's nothing much left in them but aluminum and iron. So that's where we get, and we bring it into the US and ship it up the rivers. The big smelters, Alcoa, established their factories on the rivers in Pennsylvania because they had access to river traffic, which was cheap delivery of raw materials and cheap power. Coal was plentiful. They also had factories in the Tennessee Valley. Once the Tennessee Valley was electrified with their hydroelectrics, that's cheap energy too. So you got that cheap power, then all you have to do is, how do we melt that aluminum oxide? It has to be in solution, separate ions, otherwise we can't process it. So the trick was to combine aluminum with cryolite, which is sodium aluminum fluoride. And when you do that, the melting point decreases from 2000 down to 960. So that's doable. And you just heat it up, you get it hot enough, and then you turn on the juice. And you reduce the aluminum 3+ ions to aluminum metal. And then when you're finished, you just knock the plug off the bottom, and out comes the aluminum. Then you replace the electrodes and recharge it and start all over again. But that made aluminum metal cheap. We can electroplate spoons. Actually, if you've got any silverware, actual silverware, not stainless, but actual silver, anything silver, and you want to remove the corrosion, you can take a baking dish and put aluminum foil on the bottom, and then salt water on top, and put your spoon in there, and it will remove the corrosion. I'm not sure whether it changes the silver ions to silver metal or if it just removes them. But you can conduct your own electrolysis there in the kitchen. Another industrially important electrolytic process is the electrolysis of sodium chloride. And I think calcium chloride is added to sodium chloride here for the same reason that cryolite was added to aluminum oxide, to reduce the melting point. Once you get it in, get it melted, and you adjust the voltage properly so that you don't generate, well, chlorine gas is no big deal because chlorine's from both molecules, but you don't want calcium coming off there. You want sodium only. So you adjust the voltage so that you remove sodium and not calcium. And you get sodium metal, right, out of this process, and you get chlorine gas out of the process. You can make sodium hydroxide out of this. You can make bleach out of this. There's two possibilities. These are very, very industrially important procedures, gases, gas and solid. Oh, that's it.